Okay, guys, we are starting now at 1:05. At 1:05.
So what time will the meeting start?
The meeting is starting now.
Okay,
Welcome to another session. Today we are doing partial fraction. Okay, so I'm still trying to fix my camera here. Please give me 1 minute. Okay, can you all see here? Hi guys, welcome to another session. Well, today we'll be doing partial fractions, and I hope you guys have. Today you are going to participate as compared to the last sessions or the previous sessions that we had. They were not so productive. You guys were not productive as well. But I don't know. Just see. Okay. So today we'll be doing partial fractions, as I said. And with partial fractions are pretty but at the same time, there is a lot of rules that are involved with partial fractions. Okay. So I'll just go through the most important rules, and because of time and understanding purposes, we will have to do these things in 2 or 3 sessions, such that we are able to be confident with partial fractions. Partial fractions, guys, it's easy for you to make a mistake. It's very easy for you to make a mistake. So I need to build confidence for you guys to be able to solve the type of questions. Okay. Another thing. Okay, let me do this. Another thing is, as you are going to be doing these questions, guys, okay, I'm going to need you to be able to answer most of the questions, and I'll be using your textbook. Since from last week, I've been starting to use your textbook. Let me check for questions and examples. Today we're doing, yeah. So today I'll be using your textbook, and as I said in the last session, I'll be taking only these red ones, the ones that have got the red color there. Apparently those are the hard ones, so it's better to do this example with the hard question. Okay. So without wasting any more time, let us just go through it. Okay. So with partial fractions, can you see what I'm writing here, guys? Fractions.
Yes, sir.
Okay, thank you very much. With partial fractions, we are just going to have polynomials, okay? We are just going to be having polynomials that can be decomposed or factored, okay, into a product of linear or irreducible quadratic factors. Yeah? What I mean by irreducible quadratic factors, suppose I have, let's say I have, which example can we use? Let's say I have x squared minus 3 all squared, okay? So this can be written as x squared. Okay, this is a terrible example. This is a terrible example. But yeah, the only thing that the only idea that I'm trying to give you here is that if I've got x squared minus 3, this cannot be simplified any further. If we say something is irreducible, which means we cannot reduce it anymore, we cannot find its simplest form. X squared minus 3 is its simplest form. There is nothing else we can do from there, okay? So we are saying that we are only dealing with polynomials that can be factored into product of linear or irreducible quadratic factors, such as these factors, such as x cubed or quadratic. I said quadratic. X squared minus, x squared plus 9. This cannot be reduced any further. But if I'm given x squared minus 9, this can be reduced into x plus 3, x minus 3, okay? This is a reducible quadratic factor. But this is an irreducible quadratic vector because there's nothing else we can do from that, okay? So we are going to deal with polynomials that can be decomposed into what? Into linear or irreducible quadratic vectors. I've said that 3 times. I've said that 3 times. So that's rule number 1, guys. That's rule number 1. Rule number 1 says that every polynomial can be decomposed or factored into a product of linear or irreducible quadratic factors, meaning we are going to have a factor of this nature or a factor of ax squared plus bx plus c. But this one, it cannot be simplified any further. Okay. So rule number 2 is the most important rule here. Okay. This rule number 1 is it's straight to the point. But rule number 2, you need to be aware of something, okay? For every rational function, let us say we've got a rational function f at x is equals to rx all over qx, for instance. We are going to deal with the denominator and the numerator respectively, okay? Both these functions, okay, r at x and q at x are polynomials, okay? You know what we mean when we say a function is a polynomial, okay? Now, the most important thing is if and only if the degree of this function Rx is less than the degree of Qx, then we can have, or we can express this function into simpler factors, which means that we can factorize it to give us what? To give us the linear or irreducible quadratic factors. If and only if the degree of the numerator is less than the degree of the denominator. I'm going to do examples. I'm just giving you ideas here, okay? But if the degree of the numerator polynomial is greater or equals to the degree of the denominator polynomial, then you have to use something that we call what do we call this? The long division method. Long division method. Okay. So I hope if you don't remember the long division method, today we are going to get long division method. Okay. But guys, as I always say to you, there are many ways to kill a cat and there are many cats to kill the way. So now you choose which one. Okay. So in this particular case, when we have a degree of the numerator polynomial being greater or equal to the degree of the denominator polynomial, you must make sure that your function will be decomposed in a form that f at x will be given as sx plus p at x all over q at x, where your p at x is the remainder, okay? Your p at x is the remainder, guys. Both s and p must be polynomials, okay? Both s and p must be polynomials as well, okay? So let me write that down. S and p must be polynomials. So there is a lot that I've just said, guys. With just two rules, there is a lot that I've just said. But these two rules, guys, you must always make sure that you have them in mind, because without having these rules in mind, or without understanding what the rules are saying to us, we are going to be having a problem, okay? We are going to have a problem, okay? Now, another thing that you need to know about this remainder. In this case, this remainder p at x must be less than q at x, which is the divisor, okay? This remainder must be less than the divisor, which is q at x, okay? I've said a lot, guys, okay? I've said a lot, and I know some of you are very not interested because this is mathematics after all, okay? We do not like to have so many rules and regulations and whatnot. But unfortunately, there are rules which govern things, okay? As much as we've got a government as a country, we've got rules which govern things. We cannot just solve because of the fact that this is mathematics. No, guys, okay? So let us take an example and try to understand everything that I've just said here, okay? I hope you guys have written those rules down, okay? Rule number one, yes, thank you very much, thank you very much. Rule number one, remember that the polynomial should be decomposed or factored into a product of linear or irreducible quadratic factors. And rule number two, you must check if the degree of the numerator, is it less or greater than the degree of the denominator, meaning the divisor, okay? The divisor, meaning the one that divides the other one, okay? So, should I rub this out? Yeah? Okay, let me rub it out, and then we will look at this thing again. So, let me have the first example, okay? So from the textbook, I'm going to teach you first how to decompose a function, okay? Not just any function, but a proper or improper fraction of functions, okay? What I mean by a function which is a rational function. A rational function is a function which has got some function all over another function, okay? Which is what we were writing. This is a rational function. A rational function is given by f at x is equals to a function all over another function. And both these functions are called polynomial functions, okay? So we need to know how to decompose a polynomial function, okay? I mean, a rational function, sorry. So the first question says, write out the form of the partial fraction decomposition of the function. Ne? Do not determine the numerical values of the coefficients. This question is English. I don't like such questions. No. Okay, so I don't like such questions at all. So this question and these rules, they govern four most important cases of partial fractions, okay? But today, I want us to only do two cases of these partial fractions, okay? Before we go through that example, the reason why I want us to do these cases is because I want you guys to understand what we will be doing when we are talking about partial fractions, okay? We are looking at case one, okay? Case 1 will be dealing with distinct linear factors. Distinct linear factors. Okay, guys, let me ask you a question. What comes to mind when you get the term distinct? Okay, I see you guys are going to Google. It's fine. What comes to mind when you see the term distinct? I won't move forward until you tell me what comes to mind when you see the term distinct, or you hear the word distinct.
I'd say it means something like different from the others, like it's unique.
It's different from the other, right? Which means
Yes.
you not have the same thing. Okay, thank you, my man. Thank you, my man. So when we say distinct linear factors, we mean different linear factors. We cannot have the same linear factor. It's impossible for us to have the same linear factor. Okay, then that case, when we have something of that nature, we can decompose our rational function. Yeah, we can decompose our rational function r at x all over q at x into the form a1 all over ax1. No, let me do this. It can't be x1. X cannot be different. A1 x plus b1 plus a2 x plus b2 plus so and so on. Let me just take the last time. an x plus bn. Okay. So this is what we are going to call the cover method, the cover up method. Okay. I wanna call this the cover up method. Cover up method. As I said, there are many ways to kill the cat and there are many cats to kill the way. So I'm gonna give you a chance to choose which way you want to do. Okay. But I'm gonna give you all the methods. I'm gonna give you all the methods. It's important. Okay. So we're going to deal with case 1, where we have got distinct linear factors. Okay. Then I want us to deal with case 2. Okay. Case 2, where we are going to have repeated linear factors. This is not repeated. English. Oh, my God. It's repeated. Yeah, repeated linear function factors. Linear factors. Guys, English is not my strong point. Repeated. Yeah, repeated linear factor. Okay. So in this particular case, it tells us that we can have a linear factor that is the same as another linear factor. Okay. We're going to see examples of these things. Okay. But if we've got something like this, it tells us that Rx all over Qx can be decomposed in a way that we are going to have A1 all over A1 x plus B1. Okay. Plus, in this case, guys, I want you to look at something. Okay. I want you to look at something. Here we're going to have A2 all over A1x plus B1 to the power of 2 plus plus AN and have A1x plus B1 to the power of n. Okay. So you see there's a difference between these two cases. Okay. There is a huge difference between the two cases. Okay. So in this one, I don't know what to call this. It's fine. I don't need to call it anything. I wanted to call it something beautiful, but I can't. But yeah, as these values change, you always multiply the repeated. Okay, I want you to look at something. You must always multiply the repeated factor by itself, meaning that when you have got A1x plus B1, here you're going to have A1x plus B1 squared. What are we going to have as the next term? a1x plus b1 cubed. So which means you're always multiplying this term by itself. You understand that, okay? But guys, yeah, okay, let's just take the example. Let us not confuse my students. Okay, do you understand these ideas, guys? Who's in the waiting room? No. Okay, do you understand these ideas, guys? By just explaining them, do you understand them? If you do not understand, tell me. Oh, actually, let me do it. No, let me not do it. It's fine. Okay, so let us take an example. Okay, the first example, they said we should not solve yeah, partial fraction. This is a nice method, guys. I love this. Okay, let's take an example. They say write down. Okay, let me write this thing again. Partial fractions. Partial fraction. Partial fraction. Okay. Now, the question says, write out the form of the partial fraction decomposition of the function. Do not determine the numerical values of the coefficients. Okay, that is very important. Okay, that is very important. Yeah. Okay, let me do number. There's no hard one here, guys. Hey, there's no hard question. I'm very disappointed in such questions. Okay, let me do number one. Okay, number one says that we need to find the partial fraction decomposition of 4 plus x all over 1 plus 2x and have 3 minus x. Okay, so what is the partial fraction decomposition of this? Okay, so we do have something like this, guys, okay, which is 4 plus x all over 1 plus 2x multiplied by 3 minus x. This one is already factored into linear factors. In this case, the first rule is true. The second rule is the degree of the numerator greater or less than the degree of the denominator? In this case, somebody would say, I don't know. This is how you check. If you've got two factors, which means the highest degree you have in the denominator is x squared. So my question is the degree of the numerator greater than the degree of the denominator? Yes or no?
No, sir.
No. Yes, thank you very much, my guy. Which means from here, we do not need to do anything that's got to do with long division. I'm afraid of long division myself, okay? So therefore, what we're going to do is we're just going to rewrite this in a case form, meaning we're going to write this like this, plus b all over 3x or 3 minus x, not 3x, 3 minus x. So the decomposition of the partial fraction is given by them, okay? So this becomes my final answer. This is my, okay. That was quite easy, right? That was quite easy. Let's say now I give you another one, okay? And let's say I say to you, write down the decomposition of this one. Let's say 4x minus 3, 4x minus 3, and have 2x plus the 5. Okay, so what is the decomposition of this one? The decomposition of this one is just a divided by 4x minus 3. No, I don't need to write that. Plus b all over 2x plus 5. Okay, but remember, I said to you, when you've got something of this nature, you can have something that we call the cover-up method because these terms are not the same, okay? These terms are not the same. So I'm going to further break it down for you such that you understand what I mean by the cover-up method, okay? But first thing is, do you understand what I was doing here on these two examples, guys? Or should I give you another example? Another.
I say I seem to understand because you firstly said like if you have two polynomials, then the degree of the degree the numerator is less than the degree of the denominator. Then ke mo tla applying case we apply mode.
This one.
If yes, if that's not the case, if the degree of the numerator is greater than or equals to the degree of the denominator, then long division method will apply. So
Okay, so okay, let me do this. Let me do this. Let me have a different color pen. So you are saying that the degree of the numerator must be less than the degree of the denominator. Okay. And then what did you say again, my man? The degree of the numerator is greater or equal to the degree of the denominator. Okay. So you are trying to bring this into this idea or make me understand what you are saying in that particular statement that you just said.
no, like I just say like you asked over, are we understanding it now? Like what you just did. Yeah.
Oh, so you are saying that you understand what I just did. I thought you were saying you don't understand. See, now I was ready to explain a lot.
No,
Oh,
sir.
no, it's fine. Thank you, my guy. Thank you. Okay.
Sure.
Okay. Let's have another example. Just because you guys understand. I love it. Let me take another example. Let me open the textbook. Let me take number 5. Ooh, beautiful one. Let me take number 5. Okay. Number 5 says that we must write down the decomposition of 1 all over x squared minus 9 squared. This one is very nice. So, yeah, I love it. Okay, so we have this one now. How are we going to approach this one, guys? What do you think we should do? Okay, let me give you a hint. A hint is that what does this square, the square in the denominator, mean? Okay, so what the denominator in the what the square in the denominator means is that we have repetition of factors. Okay, the square in the denominator means we have got the repetition of factors. So what is that supposed to mean? Now that's the question. Okay, what is that supposed to mean? I hear you are saying that there is repetition of factors and everything here and everything. What it means is, according to Bodmas, okay, you must always deal with whatever that is in the brackets before you do anything else, okay? Then we come with the orders. The orders, which is squared, square root, 2 to the exponent 3 over 2, 2 to the exponent 2 over 7, it's still fine. As long as the orders are taken care of, which are the squares, the square roots, and everything else, okay? So in this case, what I'm going to do is I'm going to apply the Bodmas rule, okay? And deal with the inner part. But the inner part, it's already what? Something that we call I even forgot the name of this thing. X plus 3, x minus 3. Oh, it's called the difference of two squares. It's called the difference of two squares. So every time we have something like this, x squared minus 9, we can rewrite it as x plus 3, x minus 3. Okay? So for us to continue with this, I am going to say, using the rules of, what do you call this? Using the rules of exponents, when I've got a times b to the power n, this can be written as a to the n, b to the n. So therefore, I'm going to write this as x plus 3 squared, x minus 3 squared. Okay. So we have simplified this. It is simplified to its simplest form. Okay. Now we need to write this in a decomposed manner. So in a decomposed manner, do you remember case number 2? Okay. Do you remember case number 2? Case number 2 says when you've got repeated thing. So this is where the repeated part comes. We're going to have a x plus 3, but x plus 3 comes in twice. So we're going to have b x plus 3. And I said to you, once we have got another term, we need to multiply it by itself. And the same thing applies to this one. We're going to have c x minus 3 and have d x minus 3 squared. Okay, so this becomes your final answer. So you don't see x minus 3 squared. This becomes final answer. Okay, this is the repetition of linear vectors. Okay. This is what we did. That vector, we multiplied by itself. Okay, then we did the same. So, are we fine, guys? I said under repetition, you multiply by a vector, 1 power less than the highest power. Okay, so thank you very much. Let us have another example. No. I've built your confidence now. Let's go straight to no. Let me give you another example. You see, now I'm conflicting myself now. I don't know if I should give you an example or should I give you the integrals already, but it's fine. Let me just give you another example. Because I don't want you guys to complain tomorrow and say, we didn't understand 14 because number 14 was, you see. So this time, I want you to determine the values of A and B. I want you to determine the values of A and B. So my example is given 1 all over x squared minus 5x plus 6. Write this in the decomposed. I'll give you a hint. When it's decomposed, we're going to have ax plus b plus b, we have cx plus d. Okay. What I'm saying is they are not going to be the same, which means it's a distinct linear factor. Distinct linear factor. And then you just need to solve for a and b given this. Okay. So the question is, should I do it with you or do you want to try it on your own? Because it's allowed. I want you guys to be able to gain confidence when you okay. So which one do you want? Should I do it? Should we do it together? Should we do, yeah. You always have a choice.
I think we should do it as that.
You think you should do it on your own, right?
No, it's with you.
Okay. Let me give you a hint. Okay, but it's fine. Let's just do it. Now, what I usually do when I solve partial fractions, okay, I check the denominator, especially when it's something like this. I check the denominator, x squared minus 5x plus 6. And then I factorize this, okay? Guys, let me ask you a question. Who has a problem with factorizing?
3 and 2 factors.
No, before we do that, let's understand who has a problem with factorizing such that we can deal with this problem very quickly. So all of you are fine with factorizing, okay? Okay. So let us have, we said factors are what? 3 and 2, 2 and 3.
3 and 2.
3. So what are the signs?
Negative.
Negative.
My lady. Thank you. Thank you very much.
Negative.
Negative. Okay. So therefore, this means that this 1 over x squared minus 5x plus 6 can be rewritten as 1 all over x minus 3, x minus 2, which this can be rewritten as a all over x minus 3 plus b all over x minus 2. But in this case, I said to you, please find me the exact values of a and b respectively. Okay, so what we are going to do is, now we are going into partial fractions now. Now I'm enjoying this, okay? We are going to, okay, let me do this. 1 all over x minus 3, x minus 2 is equals to a all over x minus 3 plus b all over x minus 2. So the reason why I left so much space is I want us to multiply out x minus 3, x minus 2 on each and every term, x minus 3, x minus 2. And here I'm going to have x minus 3, x minus 2. Okay? So we're multiplying each and every. Okay, let me just write this well. X minus 3, x minus 2. Okay? So we are multiplying each and every term by x minus 3, x minus 2. What are we left with on the left-hand side? We are left with only 1 because each and every term will cancel. Okay? And then on the right-hand side, what are we left with? We're going to be left with a times x minus 2. And then on this side, we are going to be left with b times x minus 3. So this is the general equation. Okay? Now, guys, please take the actually, this is a tip. Ne? This tip is whenever your factors do not have, guys, are you still there? Okay. Let me do it.
Yes, sir.
Okay, whenever you have a coefficient of 1 on your factors, ne? Whenever you have the coefficient of 1 as your factors, always use, let me write it here, always use the critical values to determine the solution. What do I mean by that? Okay, what do I mean by that? Rather than us solving these things simultaneously, what are the critical values that we have here, guys? The critical values that we have here is these ones. X is equals to 3, x is equals to 2. Then therefore, you come back here and you say, let x be equals to 2, for instance. Ne? When you let x to be 2, this changes because 1 is equal to a, 2 minus 2, which is just 0, plus b times 2 minus 3, which is minus 1. So 1 becomes minus b. Therefore, b is equals to minus 1. We do not need to work super hard because these coefficient of x are just 1, 1, 1, 1. But if the coefficient is 2 and this one is 3, do not try this at home. Okay? Yeah. But yeah, for this one, you just go through with that one, okay? You just move it like that. And then we are coming to the next one. Let x be equals to 3. Let x be equals to 3. then we're going to have 1 is equals to A times 3 minus 2 plus B times 3 minus 3, which this is just 0. You see, this one was 0 and this one is 0 now. 1 is equals to A because 3 minus 2 is just 1. Then we have solved for A and B. Then we are going to say now 1 all over x squared minus 5x plus 6 is equals to, what is the value of A? It's 1, and have x minus 3, minus, okay, let me write it like this, minus B, which is minus 1 all over x minus 2. Then we can write this as 1 all over x minus 3 minus 1 all over x minus 2. Then this becomes my final one. Oh, sorry, guys. Ish, you see excitement. Now you see. Yeah? Okay, I was super excited there. I was getting way ahead of myself. So this minus just came and multiplied with this plus, and it became this minus. Okay. Yeah. There's nothing beautiful which I just did here. Okay. So always use the critical values to determine the solution. This is going to be the safest approach you're going to take. This is going to be the easiest approach you're going to take. You're going to love taking this approach, okay? This is the easiest thing I can give to you. Only if the factors have a coefficient of what? Of 1. If it doesn't have the coefficient of 1, it will work, but it gets rather tedious. Because with myself, I don't like fractions, so it becomes a problem. But you can try it. Please do try it, guys. Please do try it. I've never tried it before. That's why I don't advise you to do it, but maybe it's because I'm lazy or something like that. Okay. So let us take an example now where we have to actually solve. No, let's take another example.
So like, sir,
Yes, my guy.
sir, like,
Yes.
like when you say like those coefficients, you meaning the coefficients of x here, like in this bracket, let's say it's A. Oh,
in the critical values.
okay.
Yes.
Must be 1 for this method to apply.
Yes.
Okay.
Yes. I've not tried
So if
the
it's
other
true,
one.
then
I've never tried with the other one. So if it works with the other one as well, I would advise you to use it. But now I've never tried it. So I don't want to give you something which I've never tried myself. I don't have much. Okay.
okay. So
Yeah. So let me give you another example. Okay. Let me give you another actually, let me give you an example which requires us, because you guys are seeing one method of this thing. I want to show you this other method where our numerator has a greater degree than the denominator. Okay, such that we see if those rules we're talking, the rules are not talking, right? Yeah, that one. Okay, so suppose now, let me see a beautiful example. Let's go. Let's do number 4 on the textbook, okay? And number 4 is given as x to the exponent 4 minus 2x cubed plus x squared plus 2x minus 1 all over x squared minus 2x plus 1. Okay, let me give you a little hint, guys. In the exams, in all the exams that I've seen, they only give such problems. So therefore, it's important for you to just deal with such problems most of the time, okay? As a tip for you to, yeah. Because in the past papers, what I've seen, they just like such questions, okay? Like the ones with big numbers, okay? So in this question, I want to ask you one question. The biggest degree, does it lie in the numerator or in the denominator?
It lies in the numerator.
In the numerator, yes. Okay, so we said, once we have got something like that, what do we use? Long division, okay? And then the outcome that we are going to have, f at x, is going to be written in the form sx plus px, which is the remainder all over the quotient. Okay. So, guys, when you're given something like this, it's important for you to check. Okay. Now, let us use long division. Long division is the divisor minus 2x plus 1. And then we have the dividend, x to the fourth minus 2x cubed, x squared plus 2x minus 1. This is a beautiful equation. Okay, so the first step when you're doing this, guys, you always divide x to the power, not power, x to the exponent 4 divided by x squared. Ne? It's x to the exponent 4 divided by x squared. The solution is x squared. We're going to write it here, okay? The solution of x squared. Then after doing that, we are going to multiply this by that. We're going to multiply whatever solution we found by the divisor. So we're going to have x to the power of 4 minus 2x cubed plus x squared. Now, the next thing that you want to do here is you must subtract the 2. You must subtract the 2. So what happens if you subtract the 2? Do you see that this term, and this term will give us 0? These ones. Do you see that, guys? Ne? So the only terms which are left is this one, 2x minus 1. Okay. So this is our remainder, which is p at x. Okay. So the thing that we have to look at now is that is the degree of p of x less than the degree of the denominator, which is q of x. Is this condition met, guys? Is the degree of the numerator p at x less than the degree of q at x?
Yes.
Yes.
Yeah. Yes. Thank you, guys. Thank you. So this one, this function here represents Sx. Okay. This function represents Sx. And it's also a polynomial. Do you agree? It's the polynomial of degree 2.
Yes.
And therefore, yes, my guy. Thank you, my guy. Thank you. So now the solution becomes x to the 4 minus 2x cubed plus x squared plus 2x minus 1 divided by x squared minus 2x plus 1. This will be rewritten as Sx, okay, plus 2x minus 1 divided by the divisor, which is x squared minus 2x plus 1. Okay. This becomes the final solution. But you know me, guys, and I always say to you, there are many ways to kill a cat, and there are many cats to kill the way. Okay. So this is what I call my lazy method. Okay. I call this my lazy method. When I'm too lazy, I use this. Now, this method goes like this. Okay. I'm to say I have x minus 2x cubed plus x squared plus 2x minus 1, and I divide this by x squared minus 2x plus 1. I'm giving you this method because I'm seeing it here, and I'm very confident that it's gonna work. If it doesn't work, please forgive me. Okay. Now, I want you to look at only these 3 terms. Okay. I want you to look at only these 3 terms. And let us take out a common factor, which is x squared. What are we left with? We're left with x squared minus 2x plus 1. Okay. And then I've got this plus 2x minus 1 divided by x squared minus 2x plus 1. Do you see that, guys? Eh? Do you see it, guys? When I multiply this by that, I get x to the 4. When I multiply this by that, I get negative 2x cubed. When I multiply this by that, I get x squared. Okay? So what happens is, do you see that this and that, they're exactly the same? So what I'm going to do is, I'm going to separate the terms and have x squared minus 2x plus 1 divided by x squared minus 2x plus 1, and we have plus 2x plus 1, or 2x minus 1. 2x minus 1 divided by x squared minus 2x plus 1. Do you see that this and that, they go to town? Okay. Then what I'm having is what? X squared plus 2x minus 1 over x squared minus 2x. Do you see that this looks exactly like that? Buffet. I'm leaving mathematics now.
Yeah, we leave it, bruh.
Okay. Okay. Do you see it, guys? I'm getting excited now. So as I always say to you guys, there are many ways to kill a cat and there are many cats to kill the way. Whenever you choose which one you want. Okay. Now I want us to do partial fractions in terms of integrals now. Now we are excited again. Am I wrong? Okay. Are we fine, guys? Are we happy with the idea? You can choose this one, you can choose this one. The solutions are the same. Ne? Oh, you can't see this one. Ne? It's x squared plus 2x minus 1. This light is, yeah. Right? Let's go back to the textbook. Let's have another question. But this time, I want us to have integrals inside. Okay? I want you to have integrals inside. As I said, I like the hard ones. Okay? So I'm gonna do number 11. This one here. Okay? I'm gonna write it down. Do you see it has the red tag here? Number 11 has that red tag. So I'm gonna do this one. And I'm gonna do number 17 as well. Do number 23, number 29. There are many. Which means you are going to have even more. Okay, are we done writing here? Should I wrap this up?
Yes, sir.
Yeah. If you didn't get it, then you can go back to the YouTube channel, check it out, and then, yeah, be confident about it, okay? But guys, let me tell you something. It's useless for me to write down the solutions for you or to do these examples for you. And then the next thing, when you don't do anything about it. And then at the end of the year or at the end of the day, you're going to see yourself not having great marks as you thought you would because you were not doing this thing on your own. After solving the whole thing, when you go and do it by yourself and then see if whether the solution is correlating or not. Do you get it? If it does not correlate, then you come back and you ask, say, how did you do number 14? How did you do number what? How did you do number what? How did you achieve that thing of separating those terms and everything like that? I'll explain it to you. I do not have a problem with that. But if you sit there and you do not ask any question, it's going to be problematic, okay? It's going to be problematic, but it's fine. At the end of the day, it's fine. Now, I said I'm going to do number 11, okay? Number 11. I'm given the points. Oh, yeah. Yeah, I must integrate from 0 to 1. And I've got 2 all over 2x squared plus 3x plus 1 dx. Apparently, this question is challenging. Apparently. I can see with you guys, this thing is easy. Because you guys, you saw things beautiful. I'm proud to have students like you. Oh, actually, we can check if that thing works, okay? Let's go. Now, I'm going to write this as 2x squared plus 3x plus 1, okay? And then I said to you, I always like to check if this thing is factorizable. 2x squared plus 3x plus 1. This becomes 2x, x, factors of 1 is 1 and 1. Everything is plus. It's factorizable. Okay? It's 2x plus 1, it's x plus 1. My colored pen is running out of color, so won't see it well. Okay, so now what you're gonna have is 2 all over 2x plus 1, x plus 1. Okay. Now, it's rewritten as a all over 2x plus 1 plus b all over x plus 1. Ah, beautiful, beautiful. Aish. Now we're gonna do that thing of multiplying throughout, but I'm not gonna write that, guys. I believe that now we have gained confidence enough that we can just multiply it by just looking at it. Okay, we can just multiply it by looking, meaning that we're just gonna have a 2 here, and what we know is that this will multiply by that and this will multiply by that. So I'm gonna have a x plus 1 plus b 2x plus 1. Okay. Are you confident with this thing, guys? Okay. Now, in the meantime, let us look for the critical values. Okay. I want us to check if it does work when our coefficient now is not 1 anymore. Then we've got negative half and x is negative 1. So let us check first. Then we know that if we check and the solution does not check out, we leave it. Yeah. So let's let x be equals to negative 1/2. I hope it works. So 2 is equals to a negative 1/2 plus 1 plus b times 2 times negative 1/2 plus 1. This is 0, okay? Because negative half times 2 is negative 1. So this is 0. So there's a 2 is equal to a times negative 1/2 or positive half. Then you multiply both sides by 2. 4 is equal to a. Oh, it works. Hey, Jesus. It works. It works. It works. Now I need to determine the condition on why it works there. Ne? After finding that condition, I'll let you know. Okay. But we're gonna check again with a different method if it does work, if it is true. Okay. But I'm seeing a solution and I'm not sure if it's gonna be the same as that other one, but it's fine. Let x be equals to negative 1. Okay. So we still gonna have that 2. 2 is equals to a negative 1 plus 1, which is 0, plus b 2 times negative 1 plus 1. Okay. So this is 0. 2 times negative 1 is negative 2 plus 1 is negative 1. So this becomes negative 2 is equals to b. Okay. We're gonna check, guys, if our a is really 4 and our b is really negative 2. Okay. And then I'm gonna find conditions on when you should use it. Okay. I'm gonna sleep tonight by finding that condition. Okay. So, okay. All right. So we found that our a is equals to 4 and our b is equals to negative 2. So let us find it with that other way, the long method of doing this thing, okay? So we have checked and it turns out to be working. Will it be correct? To experiment a bit. So let us use the long method. The long method is, I like to write it like this: ox plus 0x, not o. 0x plus 2 is equals to ax plus a, which is just multiplication, plus 2bx plus b. Okay. So we take each and every term without x, we put it together. Take every term with x, we put it together. So a plus 2b in terms of x. Why do I say in terms of x? Okay. Ax or a plus b. Okay. So a plus b is coming from here, and these ones are with respect to x. Okay. Okay. So we are going to equate the ones with x. Okay. So 0 is equals to a plus 2b, meaning that our a is equals to negative 2b. Ooh. Okay. Okay. Beautiful. Beautiful. And then we take the ones which are just constant. Constant is equals to a plus b. Okay. So let me say now A is equals to, or let me say B, I don't know. Let me say B is equals to 2 minus A. Okay, let us substitute. But why do I need to say B is equals to 2 minus A? If I can just say A is equals to 2 minus, and then have the derivative. A is equals to 2 minus, and then equate the 2 and have minus 2B is equals to 2 minus B. Okay, then we bring this B this side and becomes minus B is equals to 2. Thus, B is equals to negative 2. And it relates to the solution we got. Okay, thus, if B is minus 2, A becomes minus 2 times minus 2, which is equals to 4. It works. Yeah, I'm gonna find the condition. Okay, it's very nice, guys. We found the solution, okay? But we haven't solved the question. We haven't solved the question. We found A and we found B. What does that thing mean? Okay, we're gonna come back here, okay, and substitute it there. So for now, I need to rub this thing out, okay? Let me rub it out. So you see that this and that, these two solutions, they look the same with different methods, okay? I gave you two methods indirectly, so it's fine. So, oh yeah, this thing only applies to, oh yeah, I think I found the condition as well. I think this one only applies to distinct linear factors where you can choose your critical values as solutions. We're gonna check for that one. I don't think it works for repeated. Yeah, only works for distinct. Okay, this is the solution, okay, guys? So let us continue and write down the solution and find what is the value of A? The value of A is
The value is 4.
B is
the value
minus
of A
2
is
and
4.
A is 4.
Okay, thank you, my guy. So this becomes this 2 all over 2x squared plus 3x plus 1 becomes 4 all over 2x plus 1 and from 0 to 1 dx. So we need to do the same thing, 0 to 1 dx. Okay, so now we are going to integrate there. Somebody is going to say this is just length. Hey guys, do not do that thing. Okay, remember that when you have got something, if it's not given in the form x plus a, make sure that you use u substitution to do this solution. Okay, make sure you use u substitution to find that solution. So we're gonna let u be equals to 2x plus 1, du is equals to 2 dx, then du over 2 is equals to dx. Okay, thus here we are going to have from 0 to 1, we're gonna have, so let me just put the 4 outside here. 4, and we have 1 over u du over 2. Okay, and then here we're gonna have minus 2 times from 0 to 1, 1 over x plus 1 dx. Okay, so here we're gonna have 4 over 2. Oh, this is 2 again. We're gonna bring it here. 4 over 2 is just 2. 0. I don't need to do 0 to we're gonna have ln of u from 0 to 1 minus 2 ln of x plus 1 from 0 to 1. And this becomes 2 ln u is what? Is 2x plus 1. 2x plus 1 minus 2 ln x plus 1 from 0 to 1. Okay, it works out. It's working. Okay, so let us substitute the limit of integration, the upper limit of integration, which is 1. So we're gonna have 2 ln 2 times 1 is 2 plus 1 is 3 minus 2 ln 2 times not 2 times 1. 1 plus 1 is 2. Okay, minus, now we have the bottom one, so it's going to be 2 ln of 2 times 0 is, so it's 1, and then here we're gonna have plus ln of 2 ln of 0 plus 1, which is just 1. And we know len 1 is 0. Len 1 is 0. You can check it on your calculator. Len 1 should be 0. If len 1 is not 0, then okay, then this becomes 2 len 3 minus 2 len 2. This becomes 2. We take out 2 as a common factor. Len 3 minus len 2. This becomes 2 len 3 over 2. This is my final answer. 2 len 3 over 2. Okay? 2 len 3 over. So, as I usually say, guys, there are solutions at the end of this thing. So we're doing number 11, okay? According to the textbook, number 11 is this one. Do you see it, guys? The solution is what? 2 len 3 over 2, which is the same thing as this one. I love these things. Okay, any question? I know I've said a lot of things, okay? I know I've said a lot of. Okay.
So like say like those 3 and 2, like where do they come from? Like, yeah. I get it. Like say you. No, like this one's inside the lead. The lead.
What is this one?
Yeah.
Oh, agree. The absolute value of 3 is equals to 3. The absolute value of 2 is equals to 2. You understand? So instead of writing absolute value, I can just write 2 and I can just write 3. So I don't actually need to write absolute value because absolute value of a number is that number in a positive manner.
Yes.
Oh, how did I find them?
Like that, like this 3, like 3 and 2, like because it was X, I guess.
No, I substituted the. Oh, my lady, I'll just answer you now. Can I just explain this one, and then I'll give you the chance. You are noted, my lady. I just substituted these values, my man. What happens was for which is this one, you see. And then I did the same thing with x plus 1. Then I got 2. And then that other one I got 0. Do you understand, my guy?
Yes, sir.
Oh, I see.
Okay.
Okay.
It was just substitution, direct substitution. Okay. My lady, what is your question?
Yeah, I wanted to ask that one.
Oh, okay. So I answered both of you at the same time.
Yes, sir.
Oh, I hit 2 birds with 1 stone, or 1 stone with 2 birds. Yeah. Yeah. Now, yeah, that's the solution. I'm confident. Are you confident, guys, with the solution? We saw it. It's there in the textbook. It looks the same. Jesus is Lord. Okay. So let us take another example. I'm going to take number 17, which is a red one. I love these hard ones. These hard ones, I love them. Number 17, okay? So in this one, I need you guys to take part. Please tell me what to write, what not to write. Let's make it fun, okay? Let's make it fun. After all, this is a class lecture. It's nice. It's nice. It goes from 1 to 2. Okay, it goes from 1 to 2. So let me write down the question quickly, and then I'm gonna give a few seconds for people to finish writing that last question. Y plus 2, y minus 3. I hate such questions. They are straight to the point. Okay, let me just give you a few seconds for you to finish writing that. Yeah. So guys, so far, is it fine? Are you understanding the concept?
Yes, sir.
Yeah, we are on the right track, bro.
Okay, thank you. And then on the next session, you are going to the one for irreducible quadratic factors, and then we'll be done with partial fractions. And then, oh, we still got another integration technique. Okay, it's fine. Okay, let us solve now. Me, my blood is boiling. My boiling is blood. That sounds good. Okay. Now, we've got this question. Okay. Now we need to do the same thing, but this time they made our job to be a bit easier. Okay. Because now they told us the factors and everything. Then I can simply just skip and say, okay, you're giving me that minus 12 all over y times y plus 2, y minus 3. This is equals to a all over y plus b all over y plus 2 plus c all over y minus 3. Okay, that's what the what do we call this equation say. Okay, that's what the rules say as well. That's what everything says. Okay, they are not speaking, but just leave it. So what happens is we're gonna multiply out by the denominator. Multiply each and every term by the denominator. This side becomes 4y squared minus 7y. Is it minus 7y? Oh, yeah, it is. Minus 12 is equals to. Now, this one becomes very interesting because only y cancels out. It becomes y plus 2, y minus 3, plus b. This one cancels out. It becomes y minus 3, plus c. This one cancels out. It becomes y plus 2. Okay, this is y, guys. This is y. This is y. Okay, so I've got y. Okay, now we're gonna do our method. Let y be equals to 0, because if y is 0, then you see what happens. Okay, if y is 0, automatically this becomes 0 and this becomes 0. Okay, this becomes 0. Hey, Jesus. I got super excited, guys. Sorry about it. This becomes 4y squared minus 7y minus 2 is equals to a y plus 2 y minus 3 plus by y minus 3 plus cy y minus y plus 2. Okay. I was excited. Yeah, I just saw myself just right. Let y be equals to 0. Okay, let y be equals to 0. Okay, so if we let y to be 0, we see that all these terms, all this becomes 0, 0. This becomes 0. This becomes 0. What are we left with? Negative 12 is equals to a 0 plus 2 is just 2. 0 minus 3 is just minus 3. Okay, so minus 12 is equals to minus 6a. Okay, thus our a is equals to 2. I have yeah. And the next one, gonna let y be equals to negative 2. This is our second vector. Y is equals to negative 2. So if y is negative 2, that becomes very interesting. So we're gonna have 4 times 4, which is 16, plus 7 times 2, which is 14, minus 12. Okay, 14 minus 12 is 2, 2 plus is 18. Okay, so this side we've got 18. Okay, this side got 18. Then we come this side. You see, this one is gonna give us 0. This one is gonna give us 0. Then we're left with what? B minus 2 minus 2 minus 3 is minus 5, okay? So we're gonna have 10b is equals to 18, okay? So that's our b is equals to 5, 9 over 5, okay? Becomes 9 over 5. How many times does 2 go into 18? 9 times. Does 2 go into 10? 5 times. 9 over 5, okay? And then let us find the last one. Let y be equals to 3, which is this factor. Okay, so when you find 3 now, 4 times 3, 3 times 3 is 27. 27 plus 9, it becomes 36. Okay, so it becomes 36 minus 7 times 3 is 21 minus 12. So this becomes 33. So it becomes 3. Okay, so this becomes 3. So it becomes 3 is equals to, now this dies out, in my left with there. So it becomes C3, which is 3C, and then 3 plus that is 5, which is 15C. Okay, and then this becomes C is equals to 1 over 5. How many times does 3 go into 3 once? How many times does it go into 15? 5 times. Okay, so we've respectively found our A, B, and C. Do you want me to find it with the second method, or are you fine? Is the session out? Oh, I thought it. A is equal to 2, B is equal to 5, C is equal to 1. Okay. Do you want me to find it at the second method?
Yes, I use another method.
Okay. You guys must know in life you always have a choice. You choose. You choose. You must not be afraid to choose. Okay? Never be afraid to choose. I've got A. So this becomes y squared minus 3y plus 2y becomes minus y minus 6. Okay? Plus by squared minus 3b plus cy squared plus 2cy. Okay? Oh, it becomes 3by. Yeah, 3by because I multiply each and every time. Okay. This is 4y squared minus 7y minus 12. So this term, your now becomes a y 6 minus a y minus 6a plus by squared minus 3by plus cy squared plus 2cy, 4y squared minus 7y minus 12. Okay, so we're gonna take each and every term with the squared. So it's a plus b plus c respectively. Do you see that again? Which is y squared is this term, and this term. Then the second part, we take the ones with the y value. So it becomes negative a, then the y value here is negative 3b, and the y value here is plus 2c. This one is the y. And then we take the only term with the constant, minus 6a, 5 squared minus 7y minus 12. Okay. So as you can see, the constants are only these ones. So minus 12 is equals to negative 6a. Thus our a is equals to 2, and it correlates to that. Okay. So now, wherever we see a, we just substitute 2. Then we can solve for b and c simultaneously. Okay. So our a is 2 plus b plus c is equals to this one, 4. Okay. And our second one is minus 2 minus 3b plus 2c is equals to minus 7. Okay. Then go to b and c. B plus c is equals to 2, because 4 minus 2 is 2. Then we can say b is equals to 2 minus c. And then we take this equation, we solve it, we substitute. Then it becomes minus 3. What is our b? 2 minus c plus 2c is equals to, this becomes a positive, and it becomes minus 5. Okay. So this becomes minus 2c, it's minus 6 plus 2c plus 2c is equals to minus 5. Okay, so it becomes 4c is equals to this, and then comes which one, my lady?
Negative
Oh,
3
it's
multiplied by negative c.
3c. Yes, thank you, my lady. 3c. You see, you guys, you keep for the quiet here. And now I was gonna make a mistake. 5c is equals to, this becomes a positive, it becomes 1. C is equals to 1 over 5, which correlates to that. Then if c is equals to that, b is equals to 2 minus 1 over 5. What I usually do in such questions, I just say is 10 over 2. 10 over 5 is 2 minus 1 over 5, which is just 9 over 5, which is b. So they all correlate. You see that?
Thank you, my guy.
Yeah, thank you, my guy. Thank you, my guy. You see, I like it like this. I see, hey, I love, let's just continue. Let's just continue. Now, okay, let's continue. We've got A, B, and C. Now we need to solve for the integral. And we said that the integral from 1 to 2 is exactly equal to our A is 2 over y, okay, plus 9 over 5 over y plus 2, plus 1 over 5 all over y minus 3. Then we have this in terms of dy. Okay, so this becomes 1 to 2 of 1 over y plus, or dy, 9 over 5, integral from 1 to 2 of 1 over y plus 2 dy, plus 1/5 from 1 to 2 of 1 over y minus 3 dy. Okay, okay. So this becomes 2 ln of y from 1 to 2 plus 9/5 ln of y plus 2 from 1 to 2 plus 1/5 of ln of y minus 3 from 1 to 2. Okay. Okay. So substitution is true now here. Ne? We need to substitute. Okay. So I'm going to treat them individually. So I'm going to use 3 different pens for 3 different values. Okay. Such that we can keep the consistency. Now, I'm going to have 2. What's going on now? Is it COVID? Ln of 2 minus 1. Okay. I've substituted 2 here and I've substituted 1 here. We always subtract the 2. Okay. We always subtract the 2. Then we ln of y plus 2 is 2 plus 2. Okay. So it's 2 plus 2, which is 4, minus ln of 1. Okay. And then the last one is given by 1/5. Okay. Ln, what is 2 minus 3? It's minus 1. 2 minus 3 is minus 1. Okay. Plus ln of 2 of 1 minus 3, which is minus 2. Okay. But remembering, these are absolute values. These are absolute values. Also here, absolute. Okay. These are absolute values, which becomes ln of positive 2. It doesn't become ln of negative 2. Okay. But mind you, ln of 1 is 0. Okay. For consistency purposes, ln of 1 is 0. Okay. Ln of 1 is 0. Okay. Whew. That is a lot. Okay. Now we're going to have 2 ln of positive 2 because, yeah, 9 over 5 ln of 4 plus 1/5 ln of 2. Okay. Now if no. What did I do here? It must be minus. I said we are always subtracting the 2. So this will change the whole thing. So here. Okay. Am I correct, guys? Am I correct? Am I with you? Are you lost? Are you still with me? The only thing that sucks about this is that it's too long. Huh? It's too long. Okay. So we do have this now. Is there something that I'm missing here, guys? Because I feel like I've written everything. So here we substitute this. Okay. No. You guys are keeping quiet. I've made a mistake. Okay, made a mistake. 1 plus 2 is not 1, it's 3. Okay, made a mistake here. It's ln of 1 plus 2, which is 3. Okay. Then 1, it's 2 minus 3, which is minus 1. It's 1 minus 3, which is minus 2. Okay. Yeah. All right. Now it makes more sense. 2 ln 2 plus ln 4 minus 9 over 5 ln 3 plus 1/5 minus 1/5 ln 2. Okay. Now it makes a lot of sense. Okay, makes a lot of sense. Okay. So from here, what can we do? I don't know what to do here. But yeah, the solution will be something like this. But I want to let me solve this. I want to finish this thing knowing that I have done everything. You understand? I don't want these mistakes of doing too many things. So now let's treat the positives alone and let's treat the negatives alone. Okay. So ln 2 plus 9/5 ln of 2 squared. Okay. And if it's of 2 squared, I can take the 2 out and bring it here and have this one. Ln 3 minus 1/5 ln 2. Okay. Do you understand what I'm saying, guys? I can take this thing and put it out. Okay. So this becomes 2 ln 2 plus 2 times 9 over 5 ln of 2. Do you see that, guys? Yeah? Because of this. Okay. Minus 1 over 9 ln of 3 minus 1/5 ln of 2. Okay. Let me just move this. It doesn't move. Okay. So as you can see, we got ln of 2, ln of 2, ln of 2. Okay. So I've got many lns of 2. So I can write this as this can be rewritten as 2 ln 2 plus 18 over 5 ln 2 minus 9 over 5 ln 3 minus 1/5 ln 2. Okay. So guys, when you've got a calculator there, please tell me what is 2 plus 18 over 5 minus 1 over 5. So actually I can do this one. It's going to be 2 plus 17 over 5, which is 10, which is 27 over 5.
So he said it's 2 plus 18 over 5 minus 9 over 5 minus 1 over 5.
Yeah.
It's
Not
18 over
9.
5.
Not 9. Don't put 9. Don't put 9. It's 2 plus 18 over 5 minus 1 over 5. Yeah, it's 27 over 5.
It's
There's no way.
Yeah, 27/5.
7 over 5, yes.
I did that without a calculator. Mara. I told you I must leave mathematics, guys. Didn't I say? Okay, can you see it down here?
Yes. But there's some light there. Like after it's 2 times 9 over 5. Yeah. Ln of 2 off.
Is it fine?
Yeah.
So the solution we got there was what? 27 over 5 ln of 2 minus 9 over 5 ln of 3. And there's something which is common here. Do you agree that I can take out 9 over 5 as the common factor and have 3 ln 2 minus ln 3? Ne? Because 3 times 9 is 27, and then 9 times 1 is 9. So this thing is exactly this, okay? Do you understand the logic?
Thank you, my God.
Okay, so it's 27 over 5, which is 3 times 9 is 27 over 5, okay? And then 1 times 9 over 5 is just 9 over 5. So then this can be rewritten as ln of 3 ln of 2 can be written as ln of 2 to the power 3, which is ln of 8. So then I can just say 9 over 5 ln of 8 minus ln of 3. But according to ln laws, we can write ln of 8 minus ln of 3 as ln of 8 over 3. This is my final. Now I'm leaving this. If this is correct, okay? If this is correct, we are okay? But if it's wrong, we are ending the session. Okay. Let us check. Okay, it's number 17, okay? It's number what? It's number, I didn't, it's number 17, okay? So the solution that I found is this one. Okay?
Wow.
You see number 17 there? This one. Okay? So you can leave it at 27 over 5 ln of 2 minus 9 over 5 ln of 3. Or you can just show your lecturer that you know mathematics and write it like I wrote it. You see? Do you see, guys? These two solutions I found there. Yeah? I'm leaving mathematics today. Guys, thank you very much. I've been your tutor.
Let's end
From
the
today, I'm no
session.
longer your tutor.
Let's end the session, sir.
You're a lecturer now, sir.
Yeah, I'm about to do that. Before I end the session.
Yeah, it must be a
No, I'm ending the session. But before
Go
I'm
ahead.
ending the session, let us do something first. Wait. Let me stop the recording also. Let me take what do you call this? The class records. And for those who attended, okay. So guys, how did you today's session? Was it fine? Was it moderate? Was it productive? Was it?
It was marvelous.
Extraordinary.
Extraordinary. Wait, before you say anything, let me stop the recording because I need to submit. What are you guys saying?